Good morning, ladies and gentlemen. It's my pleasure today to talk about a novel, fast time-resolved method of temperature measurement in nanostructures. The method was developed in my lab in the Institute of Physics of Polish Academy of Sciences and allows to measure changes in temperature with resolution approaching a single nanosecond. So I can heat up the nanostructure and then trace its temperature as it cools down. It is worth pointing out at this point that thermodynamic studies of mesoscopic devices or nanostructures are not so advanced as the corresponding electrical and magnetic investigations, and this dearth can be attributed to lack of fast and robust thermometers that would be able to trace the thermal processes with sufficient temporal resolution. However, possessing such thermometers would be very desirable. It would allow to perform time-resolved calorimetry, so to investigate heat associated with physical processes. It would also be it could be utilized for bolometry, so sensing absorbed radiation, detector of microwaves, infrared or terahertz radiation. It is essential to remember that the thermal budget, understanding of thermal budget is important for failure-free operation of numerous nanocircuits involving quantum bits, squids, microcoolers, bolometers. Method of fast temperature measurement also allows to trace quasiparticles, and these quasiparticles may spoil metrological applications of single electron boxes. They degrade coherence of qubits, but for example are important for operation of bolometers. And there is also new phase coherent discipline, new discipline of phase coherent caloritronics, which manipulates with heat flows rather than with electrical currents. And last but not least, we should remember that many quantum effects can be mimicked by thermal effects, so it is essential to keep temperature under control. So let me start first with the description of my method on the particular case of tracing quasiparticles in heated nanostructures. So I will present you the heat transport due to diffusing quasiparticles, and after my main presentation in the end of it you will find some supplementary additional information which is intended to improve your understanding of the switching thermometry, which is a main tool for my experiments. So let's start. Let me start with brief summary of thermal processes at nanoscale. What are the different thermal processes that we can observe at nanoscale? So we know that electrons are at the lowest temperatures decoupled thermally from phonons. They can increase or lower their temperature by absorption or emission of photons. They may diffuse into regions of the lower temperature. They may also give up the excess energy to phonons. Here we talk about electron-phonon coupling. Phonons from the nanostructure may emit finally phonons in the substrate. Here capital resistance plays a role. So these are different very fundamental thermal processes responsible for energy relaxation of electrons, and these processes, each of these processes exhibits its own characteristic relaxation time. The investigation of these processes were carried out in steady states mainly previously. So people set their system in some steady state by heating with constant current, and they measured the increase of temperature, and they could, by fitting models, they could extract some dynamical parameters. My approach is different. I measure the evolution of temperature in time domain, and I'm going to show you my approach on the example of the process which is hot electron diffusion. So my thermometer is a superconducting nanobridge made of aluminum with e-beam lithography. It is 30 nanometers thick. It exhibits feature desired for thermometry. Already when we look at its IV curves measured at different temperatures, we see the big variation of the critical current. So the 16 milli-K, this current is much lower than at 1.2 K, and you see that in both cases the bridge superconducts until certain current threshold, and upon exceeding this threshold it is transited into normal state. The process of this transition we call switching. To measure the switching threshold with good accuracy, we apply switching protocol, which consists of sending many, let's say 10,000 pulses on the junction, and in response to each pulse, junction may switch on or remain in superconducting state. And then the ratio of the switchings to the total number of pulses gives us estimation for the switching probability. This switching probability depends on the amplitude of the testing pulse, but also it depends on temperature. So as we measure switching probability for a constant testing amplitude, and we increase temperature here in steps of 2 milli-K, we see that probability behaves, it grows with temperature. This curve can be considered as a calibration curve for the next experiment that I'm going to show you. So here we send heating pulse on the heater, copper heater. Its same photo is presented here on the left. We create non-equilibrium population of quasiparticles. They start to diffuse from the heater in the superconducting aluminum nanowire. So these red dots are quasiparticles, not paired electrons, and we expect from free particle diffusion model that in the middle the population of quasiparticles should be reduced exponentially, but for our sensor superconducting bridge we expect that at first we should see no signal, but after some time we should see onset on the particles, quasiparticles arriving to detector. And our experiment shows us that after this signal appears on the detector after 20-30 nanoseconds. So first we apply heating pulse, and then some time later, which we call here delay time, our testing pulse arrives and it probes the dynamic temperature of the bridge. We see that there is no response at first, then the signal picks up at 300 nanoseconds, and then it goes back to the initial value. So we can recalculate this temporal trace of probability into temperature with calibration curve to obtain set of curves measured at different temperatures. We see that the signal is the smallest for the highest temperature. It is because quasiparticle diffusing to the bridge are annihilated on the way to the junction by emitting phonons. We can, from this data, we can extract already the diffusion constant of quasiparticle. This is 100 centimeters squared per second, and if we increase temperature even higher to 800 milli-K, we see that signal almost disappears, but it's still visible. It picks up at amplitude of 400 microkelvin, so it's less than 1 milli-K, with blur of 100 microkelvin. So it shows that my method exhibits not only perfect temporal resolution but excellent vertical temperature resolution. And with this result, I would like to summarize my talk. I presented to you monitoring of fast thermal transient in time domain. This is not steady state investigation. I showed nanosecond resolution and 100 microkelvin accuracy. I encourage you to look at my paper more closely. Thank you. Below you will find more detailed information about my experiments. So let me first discuss the principle of switching measurement. We sent on the junction many testing pulses, say 10,000 current pulses, and in response, if junction switches in response to a single pulse, then the voltage pulse develops. So when it switches to normal state, we observe voltage pulse. But if it doesn't switch, then we observe no voltage pulse. So if the current sent on the junction is too low, we never observe the voltage pulse, and then the switching probability is 0. On the other hand, if the amplitude of the testing current is too high, in response to each testing pulse, junction switches to normal state, and the switching probability is then 1. For some intermediate value of the testing current, junction may switch, but it doesn't need to switch, so its switching has a stochastic character. So counting number of pulses junction switched divided by the total number of pulses sent on the junction gives us an estimation for the switching probability. If we now measure the switching probability as a function of the testing current amplitude, we will obtain S-shaped curve, which is known S curve. So here is summary of the switching measurement principle. Now we will use switching measurements for switching thermometry. We collect many S-curves, sweeping bath temperature in steps of 5 millik. So for each temperature we collect one S-curve, and you see pronounced sensitivity of the bridge on temperature. So S-curves for higher temperatures are collected at much lower testing current amplitudes. Already this can be treated as a calibration of our bridge, and we can also replot these S-curves in form of contour plot. This is switching probability map, revealing regions where switching probability is 1, this is this brown color, but also for sufficiently low testing current and electron temperatures we have switching probability equals 0, this is this white color. So the vertical section of this contour map is a single S-curve. Now this brown and white regions are trivial. We want to focus on this narrow band where probability is neither 0 nor 1. So let's enlarge this region. We see here that when we fix testing current amplitude, if we increase the electron temperature, the probabilities also increase from PA to PB. But we can also keep our switching probability constant and check how much the testing current amplitude must change in response to the electron temperature change. So basically we have here two methods. One method is determination of probability determination of temperature from probability, where we test our junction with constant testing current amplitudes, and we deduce that change in temperature from changes in probability. Here I plotted the inverse of the temperature responsivity. On the other hand, we can fix the value of the switching probability, say fix it at 1/2 value, and then we can measure the switching current corresponding to this probability, and this gives us another way of temperature determination. So here we have two calibration curves. Here is the switching current corresponding to temperature, and here we have responsivity corresponding to temperature. But how can we obtain the temporal resolution of the switching thermometry? We accomplish this by using pump and probe technique familiar from laser physics. So it consists of sending a heating pulse on a nanostructure, and this heating pulse is intended to create excessive population of quasiparticles to raise the temperature of the nanostructure. And it is followed by the probe sequence delayed with respect to the heating pulse, which measures the dynamic or effective temperature of the nanobridge. So for a single delay we have to send 10,000 such sequences to obtain the probability corresponding to this single delay. Then we increase delay, and again we send 10,000 pulses to record the change in temperature. So for each 10,000 pulses we obtain a single point on the temporal evolution of the temperature. And this is the way how we can reconstruct the temperature dynamic temperature profile of the heated nanostructure. So the method addresses perfectly repeatable thermal processes. Here you will find presentation of important figures of merit for switching thermometry. This is temperature responsivity and noise equivalent temperature. Temperature responsivity tells us how much the switching probability changes due to changes in electron temperature, and noise equivalent temperature sets the smallest measurable change in electron temperature. Further, you will find answer to the question whether the dynamic effective temperature measured during rapid thermal transients can be associated with the thermodynamic temperature. In next slide I present the list of publications relevant to the presented subject, and in the end I would like to acknowledge funding I received from the Foundation for Polish Science and the Polish National Science Center. Thank you.